Good morning, children. We are starting the new lesson, Semiconductor Electronics. We will start the lesson with a brief introduction about semiconductors. Okay, listen the video carefully. It is easy to understand this lesson. Okay, children, let us go to the first topic, introduction. To be able to understand the need for classification of material, first let us look at some important devices such as the vacuum tubes, which were the initial diodes or triodes, etc. These devices were used in the earlier part of 20th century in electronic circuits. First, let us try to understand the term electronics in the strict sense. The word electronics refers to the science and technology of the motion of the charges in gas. In vacuum, the motion of the charges we studied in devices called diodes or valves, and subsequently in the triodes, tetrodes and pentodes. Children, you could see the diode, triode, tetrodes, pentode images in your screen. Let us see further. Yes. The simplest vacuum tube called vacuum diode, which consists of two electrodes, is basically made up of anode, often called the plate, which is a positive electrode, and cathode or filament, which is the negative electrode kept inside an evacuated glass tube. When the cathode is heated, energy supplied to it, it helps the conduction electrons to overcome the electrostatic attraction force of the surface of the cathode, and they are set free to leave the cathode surface. The flow of electrons is controlled by waiving the voltage between the two electrodes. The vacuum is essential in the inter-electrode space of a vacuum tube, as it helps to prevent any loss of energy that would otherwise take place if the electrons were to collide with the air molecules in their path. When the anode is kept at positive as compared to the cathode, which is at the negative potential, due to the potential difference, the electrons move from cathode to anode in one direction only. Vacuum tubes are also referred to as valves. As in these devices, the flow of electrons is only one direction, that is from cathode to anode. As such, they are useful for directing radio signals. Children, you could see that electrons are only moving from cathode to anode in one direction. That's why we are calling vacuum tubes are also known as valves. Types of vacuum tubes. A vacuum diode has two electrodes, are cathode and anode. Vacuum triode has three electrodes. One is the parts of vacuum triode: cathode, plate and control grids. Tetrode has four electrodes: a cathode, plate, control grid and screen grid. Pentrode has 5 electrodes. They are cathode, plate, control grid, screen grid and suppressor grid. However, in spite of their widespread use in earlier times, vacuum tubes have certain disadvantages. We are going to see the disadvantages of vacuum tubes. First one, vacuum tubes are bulky. It operates at high voltage, around 100 volts. It consumes high power. They have limited life. The glass tubes are physically fragile. These disadvantages in the uses of vacuum tubes lead to the search for devices and materials in which the number of charge carriers and their direction could be controlled without the added disadvantages of vacuum tubes. The use of materials called solid-state semiconductor and the devices made from them called solid-state semiconductor electronic devices helps to overcome these drawbacks of vacuum tubes. As it was possible to control the number and the direction of flow of charge carriers in them, the semiconductor devices, the flow of charge carriers is within the solid itself. However, at low temperature, the charge carriers are not free to move as they do not possess sufficient energy to move. The charge carrier can be freed to become mobile charge carrier in a semiconductor by heating, applying small voltage, or exciting through light. Use of semiconductor devices has many advantages such as they are smaller in size, they are operated in low voltages, they consume less power, they have long life as the solid state material is durable, high reliability as they are less prone to microphonics. To fully understand that semiconductor device, it is important for us to understand the classification of material on the basis of their electrical conductivity. Let us see the classification of material.
Electrical conductivity or specific conductance is a measure of material's ability to conduct an electric current. Electrical resistivity, also known as specific electrical resistance or volume resistivity, is a measure of how strongly a material opposes the flow of electric current.
Solid generally classified into three types. One is conductors, semiconductors, and insulators. So conductors are very low resistivity and high conductivity.
Okay, the conductivity and resistivity based, we are classifying them into conductors, semiconductor, and insulators. Okay, conductor very low resistivity and high conductivity. Resistivity in the range of 10 power minus 2 to 10 power minus 8 ohm meter. Conductivity 10 power 2 to 10 power 8 Simon m minus 1. Examples for conductors: copper, nickel, etc. Insulators very high resistivity and very low conductivity. The ranges of resistivity is 10 power 11 to 10 power 19 ohm meter, and ranges of conductivity is 10 power minus 11 to 10 power 19 Simon meter minus 1. Example of insulators are wood, rubber, etc. Then let us see about semiconductors.
It has resistivity and conductivity lies in between that of metals and insulators. Thus, they have lesser conductivity and higher resistivity than metals and higher conductivity and lower resistivity than insulator. The resistivity ranges from 10 power minus 5 to 10 power 6 ohm meter. Conductivity ranges from 10 power 5 to 10 power minus 6 Simon meter minus 1. Okay, children, note down this one. This is there in your physics book. Example of
semiconductor, silicon and germanium. Note down all these tables. Okay, children.
Into two different group. One is elemental semiconductor. Next one is compound semiconductor. Elemental semiconductor are single elemental semiconductor. They belong to fourth group of modern periodic table of elements. Generally, will have silicon and germanium are the most commonly used elemental semiconductors. Compound semiconductors are found by using two or more elements. They are synthesized using elements from groups 2 through 6 of the periodic table. Semiconductor.
Okay, we'll have three type of compound semiconductors. Inorganics, example for inorganic: cadmium sulfide, gallium arsenide, and cadmium selenide. Organic compounds: anthracene, doprethalocyanine. Organic polymers, polypyrrole, polyaniline, and polythiophene. Okay, these are the examples of compound semiconductor childrens. Let us see. Okay, note down all these things. It's very important. They may ask in 1 mark. Okay, it's a reading homework, children, based on the energy bands. We'll discuss in the next class. You read line by line and understand the concepts. You should know what is conduction cell, what is valence cell, what is electronic convey, everything. You should know yourself. Collect all the information about conduction cell, valence cell, what is energy level, everything. Then we will discuss in the next class. Okay, children. Now we will see about intrinsic semiconductors.
Children, in this chapter, we will restrict ourselves to study of inorganic semiconductors, particularly elemental semiconductor, silicon and germanium. Only we are going to see about silicon and germanium only, children. On the basis of energy band, as I told you earlier, it's a homework, reading homework, to read line by line and understand what is what. Then we will discuss in the next class. Now, we will move on to the 14.3 topic, intrinsic semiconductors. Okay, it's very important. We have two types of semiconductor. One is intrinsic semiconductor and other is extrinsic semiconductor. Here, intrinsic semiconductor is a pure semiconductor. We'll see further about intrinsic semiconductor. A semiconductor without any artificially added impurity is called an intrinsic semiconductor. Both silicon and germanium, the two most commonly used semiconductor. Let us take a look at the atomic structure of silicon and germanium. Both silicon and germanium have 4 valence electrons. So let's see the atomic structure of silicon and germanium. See that atomic structure of intrinsic semiconductor. Silicon have 284 and germanium 218.4. Both are having 4 valence in outermost orbit. In crystalline form, each silicon and germanium atom uses its valence electrons to form 4 covalent bonds with 4 surrounding atoms. You could see in your screen. Let us use the crystal structure of silicon to further study intrinsic semiconductor. Remember, following discussion applies equally to germanium in its intrinsic form. Okay, children? Now check your book and see 14.3 topic. Each atom is surrounded by 4 nearest neighbors. We know that silicon and germanium have 4 valence electrons. How it forms a crystalline structure, children? Very simple. By sharing the electrons with neighbor atoms. How it is sharing the electrons? By covalent bonds or simply valence bond. The two shared electrons can be assumed to settle back and forth between the associated atoms, holding them together strongly. Okay, children, you would have learned in your chemistry what is covalent bond, what is ionic bond, all those things. You know that when I can say the atom is completely filled, whenever the outer cell is filled with 8 electrons, I can say that it is completely filled. Now you see, children, you can see the schematic diagram of silicon in figure 14.3. Clear? It shows the idealized picture in which no bonds are broken. Such situation arises at low temperatures. Clear? So all the bonds are, all the atoms are bonded with each neighbor atoms. There are no broken bonds. Clear? What will happen when the temperature increases? As the temperature increases, more thermal energy becomes available to these electrons, and some of these electrons may break away. Clear? What will happen when we are giving energy to the silicon atom? That is silicon crystal. Now we should not say silicon atom. We have arranged silicon atom such a way the silicon atom formed silicon crystal. Okay, how it is becomes silicon crystal? Very simple. It is formed covalent bond nearby atoms. Clear, children? The thermal energy effectively ionizes only few atoms in the crystalline lattice and creates a vacancy in the bond as shown in figure 14.5a. Clear? We will see. So what will happen when we are giving heat energy to the silicon lattice? What is a silicon lattice? Very easy, children. When we are going for a chalk piece contains more number of atoms. I will take one layer of that chalk piece atom. This is nothing but lattice. Here, so I am arranging the atoms in a row wise, always column wise. I could say that it is a silicon, or it is a lattice. Now you see the figure 14.5. It's a 14.5. Okay. Sorry. It's 14.5a. Here, see that all the silicon atoms is formed covalent bond with neighboring atom. I've taken only the one layer of silicon atoms. I could say that it's a silicon lattice. Okay, let us see how can we make the intrinsic semiconductor to conduct electricity. Very simple. Already, as we discussed, I have supplied heat energy to the silicon atoms. It will break the covalent bond. There will be a free electron. That is called thermally generated electron. That means one electron came out from a covalent bond. There will be a vacancy. The vacancy is known as holes. Clear, children? The vacancy in the bond is known as holes. The holes behaves as apparent free particle with the effective positive charge. I could say that the vacancy created by the electrons is known as holes. Hole is nothing but positive charge. One electron going out of the covalent bond means there will be a one hole. That means number of electrons will be equal to number of holes, which is equal to Ni. That is known as intrinsic carrier concentration. That means one free electron is coming out from the covalent bond, there will be one hole. That means number of electrons should be equal to number of holes, which is equal to Ni. That is known as intrinsic carrier concentration. Semiconductors possess the unique property in which, apart from electrons, the holes also moves. Let us see how we can make the holes to move from one place to another place. Okay, children, underline these words. Suppose there is a hole in site 1. See the diagram 14.5. The movement of holes can be visualized as shown in figure 14.5b. An electron from a covalent bond at the site 2 may jump to the vacant site 1. You see that 14.5. Clear, children? 5a, you see there is a vacancy created by thermally generated free electron. Why we are saying it is a thermally generated free electron? Because I am supplying heat energy to remove the electron from the covalent bond. It absorbs heat energy and it creates The electron vacancy, we are calling that vacancy is hole. Clear, children? There is a site 1. Now you could see in figure 15.3 what is happening. From neighboring atom, electron would jump from site 2 to site 1. Why it is happening? Very simple, children. In order to make a stable atom, from one atom to neighboring atom, electron is having. So what is happening? From site 2 to site 1, electron jumps. Then now where is the vacancy? Vacancy is there in site 2. Similarly, what will happen? Slowly from some other place, the electron will jump to site 2. Then what will happen? There will be a vacancy in site 3. Same way, some other site 4 to site 3, the electron would jumps. Then there will be a vacancy in site 4. Then automatically what is happening in silicon crystal? Now I'll read. See, children. Therefore, apparently the hole has moved from site 1 to site 2. Note that electron are originally set free. It is not involved in this process of hole motion. The free electron moves completely independently as, underline this word, children, the free electron moves completely independently as conduction electron and gives rise to an electron current, i.e. see how I am generating free electron. Very simple. In supplying heat energy, there will be a free electron. The electron which is come from breaking of covalent bond. Due to the motion of those free electron is there will be electric current. That current is called IE. Now you know that if the vacancy is created from one place to another place, the electron would jump. Due to the movement of the holes, there will be a current. That current is known as IH. Clear? Under the action of an electric field, the holes moves towards a negative potential, give the hole current IH. What is the total current, children? Very simple. I equal to electron current plus hole currents. Clear? Then underline this one. It may be noted that apart from the process of generation of conduction, electron and holes, a simultaneous process of recombination occurs with the electrons recombine with the holes. At equilibrium, the rate of generation is equal to the rate of recombination of charge carriers. Recombination occurs due to an electron colliding with the holes. Clear, children? Very simple. One electron is coming means there will be a one hole. Two electrons coming means there will be two holes. That means whenever these electron holes are meeting, that is known as recombination. The atom becomes neutralized. Clear? At equilibrium position, the rate of generation and the rate of recombination will be same. Underline this one. This is very important one. Clear? Let us see the animation part now. Okay. See this one, children. Very simple. I am supplying heat energy. There will be a thermally generated electron. The vacancy created by electrons are known as holes. Free electron holes are created. As I told, in a intrinsic semiconductor, number of free electrons always equal to number of holes. Now you see the animation. In position 1, there is a hole. Now from the position 2, electron can jump to position 1. Because of movement from position 2 to position 1, there is a vacancy in position 2. An electron from position G jumps from 3 to 2. What is happening? Ultimately, the holes are moving. Clear? That means there will be a two current. One current is due to the free electron, another current due to the holes movements. Clear? Keep it in your mind, children. The movement of holes only occurs due to the electric field. Clear? There is no relation between the free electrons and the holes. Clear? What are the charge carriers here, children? Free electrons will move those electrons generated by the thermal energy. Then there is a movement of holes. That means there are two charge carriers are there. One is electrons, another one is holes. Then what is the total current? In thermal equilibrium, underline this word, children. Note that the electron originally set free. It is not involved in this process of hole motion. The free electron moves completely independently as a conduction electrons and gives rise to a current. The current is known as IE. That is the electron current. Clear? Then one more line. Under the action of electric field, the holes moves towards the negative potential, giving hole current is known as I hertz. What is the total current? I equal to IE plus I hertz. Clear, children? Next class, we'll see the extrinsic semiconductor. Then on the basis of energy bands, how can we classify the material? Very easy chapter, children. See the video again and again. If you have any doubt, you ask. Okay, children? Thank you, children. Take care and read the semiconductor lesson line by line. What are the homeworks? Read the introduction, and which is there in your page number 467, 468. On the basis of energy bands, it's a homework, reading homework, read line by line. And what are the difficult terms are there? Find out it from your chemistry book. We'll see in the next class. Then we have completed 14.3 intrinsic semiconductors. If you have any doubt, you ask me. Come to the chat box and ask your doubts. I'll clarify the doubts. Clear? Energy bands, we'll see the next class. The next class we are going to see extrinsic semiconductor, then energy band of intrinsic semiconductor, extrinsic semiconductor, then pure semiconductor, p-type, n-type, everything we are going to see. So very easy lesson, children. Read line by line, then you can understand the topics. Okay, children, thank you. Take care. We'll meet you soon. Bye.